Thanks for the introduction. I'm Jian from WiNLAB Rutgers University. I'm really glad to share our recent research, personalized fitness assistance using Wi-Fi. So people always care about their health, and nowadays the accelerated pace of life and the increasing work pressure have compelled many people to adapt to this sedentary lifestyle. And such a sedentary lifestyle has a negative impact on our physical health and often lead to many chronic illness such as obesity. As a result, there is an increasing need for people to exercise regularly to stay healthy. However, there are few workout options, especially for those work-at-home people or office workers, because sometimes it will be very hard for them to squeeze time to go to gyms. So more and more people gradually resort to homes or offices to exercise to maintain their health, which is more convenient for them. And this doesn't require any constraints of space or time. Actually, many exercises can be done in home or office environments, such as this squat, stretch, riding a bike, or even the free weight with dumbbells. And in addition, the exercise monitoring is also very important. It's very common that people cannot always stick to their fitness plans due to the lack of guidance in home or office environment. And also the incorrect human body movements or body postures may degrade the efficiency of training and may cause very serious injuries. So it becomes very necessary to track the user's fitness or exercise and let users know whether they follow their fitness plans or whether their body gesture, body posture are correct or appropriate. So let's look at some traditional fitness assistance. We can always hear a personal coach. However, this is very costly and is mostly not available in office or home environments. Also, the other solutions such as video or app instructions can provide guidance at some levels. However, they cannot record anything about our exercise. They cannot evaluate our exercise. They cannot provide any feedback with users either. So it's highly desirable to have a system that can obtain the workout statistics and perform a workout assessment. Also, this desired system should be able to not require any attached sensor on the human body and also incurs minimum involvement from the people. We have a previous work. We propose a solution using wearable devices. The basic idea for this system is to record the motion sensors on the wearable devices and explore the capability of deriving fine-grained exercise information, such as we can use these motion sensor readings to recognize the type of the exercises that the user did and count the number of repetition or number of sets the user did during the workout. And also, this system can assess the dynamic postures, including the movements pattern or positions, because the intuition behind this system is that such repetitive body movements can be captured by the inertial sensors on the wearable devices, such as the smartwatch. And then we'll use these motion sensor readings to recover the body motions to further estimate the type of exercise and do the exercise evaluation. And those sensors on the wearable devices or mobile devices include the accelerometer, gyroscope, and magnetometer. And this system can obtain the workout statistics and also can evaluate the workout. However, this system still requires the user to wear a device on the human body, so it's not always convenient for people. So different from existing solution, in this work, we would like to have a system, contactless smart fitness system, which is a device-free, non-intrusive, because we want to satisfy these two points by reusing the existing Wi-Fi infrastructures. All the devices used in this system is commonly used Wi-Fi device, just this router, laptop, or even a smartphone. So everyone has one, every family has one. The basic idea is that the Wi-Fi signal is everywhere, especially in the home environment or office environment. And the Wi-Fi signals around us could be easily affected by our body motions, so that we can capture some measurements from the Wi-Fi channels to detect this body movement, so that we can use these measurements to detect movements and recognize the movements. To be more specifically, in this work, we use a fine-grained channel state information because it can provide both amplitude and phase information over multiple OFDM subcarriers. Because Wi-Fi standard is based on OFDM system. And in an OFDM system, we can model the whole channel as Y equals HX plus N. This X is transmit signal, N is noises, and Y is receive signal. And this H is so-called channel state information. It can be estimated by y over x. So if there is a person moving in the Wi-Fi sensing area, if there's a person performing exercise in the room, this age can change a little bit, so that we can use this variation, the CSI variations, to detect the body motions, to estimate the types of the human exercise. Regarding the exercise, it usually consists of repetitive movements, which can be used to provide statistical information. For example, people are always interested in knowing the number of repetitions and the number of sets they did during the workout. For example, in this bicep curl, the one up and down movements is called one repetition. And the group of consecutive repetitions is called one set. So this information is very important for the workout statistics. Also, the different exercises have a different, involve different body movements. So it has a different impact on the CSI readings. So we can extract the unique features from the CSI to uniquely identify the type of the exercises. So for our system overview, our system first takes as input a time series of the CSI amplitude from a single pair of Wi-Fi devices. And then our system performs workout identification to differentiate workout activities from non-workout activities. Then our system performs this spectrogram analysis by converting the time series CSI amplitude into the time frequency domain. Then this spectrogram information will be fed into two components in our system. One is the workout interpretation. We have a segmentation and counting, workout recognition, and people identification. We use these modules to obtain the repetition segments, and also we can count the number of repetitions and the number of sets the user performed during the workout. We also use the DN model, deep neural network model, to recognize the type of the exercise and associate this recognized exercise with corresponding user, because we have this people identification model. On the right part, we have a workout assessment. It contains two modules, repetition speed and strength estimation, and workout review, which are very useful in the quality review, quality evaluation, and the abnormal workout detection during the workout. And the output of our system contains the number of repetitions, the number of sets, and the type of the exercises the user performed. And also we define two metrics, work to rest ratio and repetition tempo ratio, which are used for evaluation of the workout. So in order to detect the workout activity, we first need to identify the unique features in the CSI readings associated with these workout activities. We conduct one preliminary experiment by recording a series of activities performed by a specific user in an office environment. So this user is first typing in front of the computer, and the user walks to a location and performed 5 repetitions of the lateral raise. And then that user walks back and continues typing. So this figure shows the CSI amplitude along with the time series, along with the marked time frame of each activities. And from this figure, we can see only in this workout session, during this time period, we can observe the repetitive patterns, because in this session, in this time period, the user is performing the repetitive body movements. So in order to detect the workout activities, the question here is converted to how to detect repetitive pattern in the CSI readings. So in our algorithm, we first use a sliding window on the CSI readings. We then perform the offset removal by subtracting a fitted low-order polynomial train. And after that, we use the autocorrelation, and we set empirically set a threshold 0.2. We can see in this figure there are 5 peaks indicating that we have 5 repetitive patterns in the CSI readings, so that we can use this algorithm to detect whether this segment contains workout activities or not. For the segmentation and counting, we look at the CSI reading in a different domain, in this time frequency domain. From the top figure, it shows a spectrogram of the CSI readings. In this experiment, we ask one volunteer to perform the 4 sets of the lateral raise, and each set contains 5 repetitions. So totally, we have 20 repetitions in this example. So in this figure, in this frequency time domain, we can clearly see the repetitive pattern in the SSI readings, and then we accumulate all the power spectrum density along the frequency components, and we use the short-time energy in the window to make this curve more distinguishable. So with this curve, we can easily obtain the starting point and the ending point of each repetition, so that we can get the segments of each repetition. And also, based on this curve, we can count the number of repetitions that the user did and the size of the user did. So with the information of the repetition segment, we can extract features from the segment and put the feature into a machine learning model to identify the type of the exercises the user performed. And one thing I also want to emphasize is that in this task, we also need to differentiate different users, because for the same workout space, it could be shared with multiple people. For example, it could be shared with multiple family members in home or multiple colleagues in office. So we proposed the two-layer deep learning DN model to recognize the types of the exercises the user performed and associate this recognize the type of the exercises with the corresponding user. So we proposed a two-layer DN model, and each layer contains one autoencoder and one softmax classifier for workout interpretation and individual identification, respectively. And also for the feature extraction part, we extract 8 time domain features from each OFDM subcarriers. Because from the Wi-Fi card, currently we can obtain the information from 30 subcarriers. So here, totally, for each individual, we can obtain 240 features, and we feed these features into the machine learning model. And during this model, in the first layer, we can obtain the type of the exercises, and also in the second layer, we can know who performed these exercises. For the workout assessment, we want to first analyze this based on the repetition level, because one repetition usually consists of body movements from an initial position to a final position, and then back to the initial position. That is commonly structure of this repetition. For example, for the bicep curl, you first put your arm at the initial position, and then to the final position, and your arm should be back to the initial position. That is one repetition. And here, this figure shows the spectrogram of the SSI readings with the body movements. So we can clearly see this initial position and to the final position, and then back to the initial position. So one thing here is that the good exercise should maintain a consistent rhythm, so that the user can well feel the weight or control the weight to improve the efficiency of the training. So in this work, we define 2 metrics to quantify the quality of the workout. The first one is work-to-rest ratio. That measures the ratio between the time of the repetition and the following time of the rest. So in this equation, the modulator is how much time is spent on each repetition, and demodulator is the time duration of its following rest. And the second metric is the repetition tempo ratio. That means the tempo or speed at which a user performs the repetition. And the modulator here is the time duration from the initial position to the final position. And the demodulator here is the time duration from the final position back to the initial position. So to improve the efficiency of the training, we need to let the user try to make these ratios consistent and stable. So with the workout assessment, our system needs to provide a reasonable recommendation with the users. For example, these 2 figures shows our workout assessment plan after the user finished the 12 repetitions of the lateral raise. And the user can observe how each of the repetitions is performed based on this work-to-rest ratio and the repetition tempo ratio. So from the left figure, we can see on this 7, 8, or 9, these 3 repetitions is over the upper bound. That means the user completes the repetition too fast. And for from the right figure, we can see this repetition, the 10th repetition, is lower than the lower bound. That means that user has a low speed from the initial position to final position. So after the workout, after this set of the exercise, the user can visually see how they performed, how the user performed these repetitions. And this user can always adjust his subsequent repetitions by paying more attention to these repetitions that are poorly performed. And in the experiments, we conduct extensive experiments to evaluate the performance. Specifically, we chose 10 representative indoor exercises ranging from this standing bicep curl, lateral raise, lat stretch, tai chi, and body extension. And also, we use 2 laptops as the transmitter and the receiver to create Wi-Fi links. And here, we didn't modify any hardware. We just installed the Intel 5300 Wi-Fi card on this laptop because actually we did lots of engineering work to turn the Wi-Fi card to the debug mode so that we can easily obtain the CSR rating from the Wi-Fi card. But this CSR rating is a readily available value in all the Wi-Fi devices. So if it's a supported Wi-Fi, we can get the CSR rating from the device. And for the data collection, we recruited 20 volunteers, including 18 males and 2 females at 3 different indoor locations, 1 living room, 1 bedroom, and 1 office space, and over 10 months time period. And we use the following metrics to evaluate the performance: recognition accuracy, precision, recall, F1 score. So for the DN-based personalized workout recognition, we showed 2 confusion matrices here. The one is for the workout recognition. The other one is the individual identification confusion matrix. So for the workout recognition, our system can achieve over 93% accuracy, and the corresponding precision recall and F1 score are about 90%. That demonstrates our system can effectively recognize the exercise, the type of the exercise the user performed. And also our system supports the user identification because the different users have a different body shape, different weight, so that has a different influence to the Wi-Fi signals. So we can use this this impact to differentiate the different users. So for the people identification, we can achieve over 97% accuracy among 20 users. So we also evaluated the impact of the different heights of the device because we want to place, the Wi-Fi device could be placed at anywhere. We tried the different settings like the floor, table, furniture. We used the 1.3 to refer the place on the top of the cabinet, and the prong 2 is on the floor, and the prong 8 is on the table. We evaluated our system at different settings, and all the settings can have comparable high accuracy. And also the people identification can still can achieve 97% accuracy. So demonstrate this result is very encouraging because we didn't use any additional hardware. We didn't attach any sensors on the human body. All the devices we used are the commonly used Wi-Fi devices. We create Wi-Fi links and use Wi-Fi signals to help user automatically count the number of repetitions, assess of the exercise. And also we can review, we can evaluate the exercise to see how good the user performed. To conclude our work, this work is the first work of using Wi-Fi signals in this domain, in this fitness domain. And we demonstrate the channel state information in Wi-Fi signals can be used to capture this body movements to further help people with their fitness, with their exercise. And also we propose a DN model. We put the features from the Wi-Fi, from the CSR readings to the model, and we can recognize the type of the exercise that the user performed, and also we can identify the user who performed this, and to know who performed this exercise. And also we performed extensive experiments over 10 months, confirmed the robustness and effectiveness of our system. Yeah, that's all. I'm glad to take any questions. Thank you.